Mhm. Thank you, Dr. Ismail, for that introduction. So, what is a quantum network? That is the essential question I have to answer before I can talk about individual elements in such a network. So we define a quantum network as being a network which distributes entanglement over large distances. And this has been a story that has a long history. First, we have, sorry, my menu is in my way. In the 80s, Wiesner started discovered that information can be encoded in polarization and sent over different networks. Further on, Bennett and Broussard started the field of QKD, of quantum key distributions, using their protocol. Baumeister and et al. In the Zeilinger group created teleportation in the 1990s. And finally, by the year 2008, the quantum technology has developed so much that Jeff Kimball could write an article in Nature envisioning what a quantum internet would look like. The difference now is that large-scale networks are becoming a reality, and I believe within the next decade we will see this. The reason behind this is that we are making, there's many people who believe this. In the US, over $500 million has been invested, and this is an old number. There's all kinds of acts that Congress passes. In Europe, 1 billion euros has been set aside for the quantum flagship program. In China, there's an institute that focuses on quantum technologies, and over a period of time, they are planned to invest over $10 billion. Roughly half of this money is going to quantum networks. And South Africa is also launching, or launched in March, a quantum technology initiative. I couldn't find much details about it, but I'm sure it's very exciting. So why we can do it is because there has been improvements on the small and large scale of quantum technology. For example, on the small scale, individual atoms can be interacted with through cavity QED. I know a lot of you are familiar with the superconducting qubits and circuits, for example, from IBM. And then also another competitor in the quantum processing regime are trapped ions that has successfully done a lot of simulations and also some processing behavior. On the large scale, we have the Chinese that has launched a quantum satellite. We have large, long distance Bell state inequality violations. And finally, LIGO is also a big interferometer experiment, and non-classical light is part of their future plans to improve accuracy. But in order to really scale up a quantum network, we cannot use traditional amplifiers due to the quantum no-cloning theorem. So one protocol in improving this limitation or overcoming it is a quantum repeater. A quantum repeater starts off with two entanglement sources, each producing a pair of entangled photons. These photons are stored in quantum memories for synchronization. Once we are ready to retrieve them, we can send them out with the two central photons interacting as the Bell state measurement. This projects out into an antisymmetric Bell state, which entangles the two far apart photons. This is really important to know, that the two particles that are now entangled never physically interacted. And this can establish that large-scale network that we want. So the outline of the talk is going to follow as follows. Scalable quantum networks that we build in Stony Brook, that's based on room temperature qubit memories, how we interconnected them, and then also some progress that we're working towards processing nodes in the quantum communication framework. Finally, I'm going to just give a brief overview of some future single photon sources that we work at ETH. Visually, I want to indicate it following the quantum repeater protocol. The first section will talk about quantum memories. The second section asks the question, what if we can change the current Bell state measurement that is probabilistic to something that is more deterministic by using a quantum processing node? And finally, I want to talk about the entanglement sources. So how do we get from flying qubits to storage? Now, flying qubits, in our case, optical photons, are ideal carriers for quantum information. We can encode the quantum information in polarization, in spatial modes, or in time band modes. Light is already used in fiber optics, so the infrastructure exists. So this is a very good system. However, to store them is pretty difficult because one needs to controllably slow down, then store it, and then controllably retrieve it. The system that we use is called electromagnetically induced transparency, or EIT for short. This is based on the interference between two decay channels created by a strong control field and a weak probe field in the lambda scheme in a well-behaved atom, in our case, rubidium-87. What EIT does is that it changes the dispersion and the transmission profiles of the medium. What the dispersion with a quick change that's shown by the blue does, it slows the light down and it compresses the pulses. But at the same time, the medium becomes transparent on the two-photon resonance, and that gives the transparency. The transparency allows us to map the photonic state completely once the control field is on, so it enters the medium while the medium is transparent. It's mapped onto the atomic excitation, and once it is, wants to retrieve, the control field is switched back on. Now, how this looks in practice is the following. We use polarization encoded qubits and split them into two rail base qubits with a beam displacer. Each rail is then stored in the medium as shown before. And once they are combined again, we can characterize the polarization qubits again using single photon counting models. The storage looks like this. The light blue curve is the input pulse. The unstored pulse is this blue peak in the front. That's part of the process that causes the adiabatic transformation together with the control field. And then the retrieve pulse is shown here. I also indicate the storage signal compared to the background signal in two different colors. In this picture, you can see that the background is pretty high still. And this is why in our first paper, we didn't reach the levels that we wanted to reach of fidelity. We started modeling the noise of the system based on starting with cold atom models and then adding kinetic terms and then changing the tuning of where we store. We realized that we can optimize the memory to a signal to background ratio of up to 6, where before we had 1.5. Simultaneously, if we look at how the different polarizations are retrieved here at the retrieving end, you can see that all of the different polarizations are retrieved at about the same efficiency. This is critical for universal memory. This allowed us to achieve 86.6% fidelity. This is above the threshold for a quantum memory for the attenuated coherent states that we used. And remember, this is in room temperature. We also experimented with adding interactions with auxiliary fields to combat the noise that is generated and which we modeled. If you look at the figure on the top right, we see a beating that results in the auxiliary field. If the phase of this beating is chosen correctly, we get a very small background signal compared to the rest. With this single rail experiment, we expect the estimated fidelity to be above 90% once such an experiment is done. We can also increase the storage time by changing the buffer gas. And where we did the experiments I showed before, sub 1 microsecond, we see storage to up to 50 microseconds. Now, how do these memories behave in a quantum network setting? We, together with collaborations from Padua University, created a mock-up of a network that's inspired by the BB84 protocol. We start with the Alice module that turns a random string of numbers into different polarizations using an FPGA and AOM module devices. Then we have a quantum channel of 20 meters between two labs in free space. We detect these and, well, we couple this to fibers and then store it in the memory as shown in the previous slides. And finally, we now characterize it using two sets of SPCMs based on the different bases of the polarization. So what we see from this experiment is that we have very good discrimination between the two polarizations of H and D or DNA, depending on the basis that the photons were sent. Since our memory is around 88% efficient in this fidelity of 88%, we have a key generation rate that falls outside the region of a positive key generation rate once all the efficiencies are taken into account. However, if we include the auxiliary fields that we talk about, we predict that we can reach a quantum bit error rate of 3, which will put us in this colored region, which has a positive rate. So to summarize what happens in a network is that the memory can store random qubits that's switched fast. We have the potential of a low quantum bit error rate. This is compatible with QKD and a protocol that uses memories such as MDI QKD. And because the phases between the polarizations are stored successfully, this is suitable for entanglement. Now, an update of this experiment in the network setting, 2 of these memories were used to do an interference experiment with the Honger-Mandel, where the 2 photons were stored in the 2 different memories and then interfered. As you can see, this the fellow lab members did that after I left. So with the quantum memories working within a network protocol, we now can move on to the second phase of the talk. So while quantum processing and quantum communication are often thought of sort of separate ideas in the quantum technology sphere, the relationship between communication and processing is not a new one, because the transistor actually originated in research that was to try and replace amplifiers and switchers in the Bell telephone system. The current way that we do Bell state measurements, as I mentioned before in the quantum repeater protocol, is probabilistic because it's based on a beam splitter. However, a lot of people have worked on moving towards something that's more deterministic. The Rayner-Blatt group did a swapping of entanglement in ions already in 2008, and groups that are looking to reduce the probabilistic nature, not necessarily canceling out completely, are the Rempe group and the de Riet-Martin group. So the first foray into this research was that we characterized an optically controlled nonlinearity. In the interest of time, I'm not going to go through the paper's full process tomography. I just want to highlight 2 aspects of this experiment. By adding an extra field that's indicated in green to the lambda scheme that I showed for EIT, we call this extra field a signal field. We can change the behavior of the EIT, specifically how we characterize it with quantum state, coherent state quantum process tomography. That was that the pseudo probability density of the coherent states can be identified, and the slowdown phase shift, EIT only, and the optical curve phase shift after the signal field was added. And we see the difference in this of this angle of the phase indicated due to this process. And also to highlight, this was done in the room temperature experiment. But now we wanted to move towards something that is more unique and a dual connected node. And our inspiration came from two different fields. First, the ensemble behavior that we see in the memories, together with the quantum abilities that EIT also call related to that, the dark state polaritons, and then this N-type scheme that I showed before gives us, and the fact that the cooling techniques of atoms are pretty well understood. Furthermore, optical cavities have interesting properties when interacting with atoms. The Purcell effect shows that the environment changes that the atom sees, and in the strong coupling regime, such as the James-Cummings model, reversible coupling between the atoms and photons are possible. So what we built was this perpendicularly layout setup of two cavities coupled to a cold atom ensemble. So how we went about this is we started with a magneto-optical trap. There you have to have two beams of the cooling and the repumper. And then this enables, together with the quadrupole magnetic field and scattering forces, to cool and trap the atoms. Just a brief overview, because I know some of you are very aware of how this works. Red detuned lasers causes atoms that move against the laser beam to be Doppler shifted into resonance and therefore slow down. We need to do this in 3 dimensions in order to make the slowdown complete. Adding the quadrupole fields gives us a position-dependent force. So the force equation becomes something dependent on velocity and position, which is an overdamped oscillator and therefore trapping the atoms. There we have a little cloud appearing for showing the atoms. Now the mod that we worked on was a commercial mod given by, or not given, that we got from a company called Quanta. At 2013, they advertised it as the smallest mod setup in the world. However, a unique thing for our system was we had to get access to the optical cavities, and therefore the whole system had to be rotated, and this added to the alignment complexity. So just again, how this would look, or this looks, is that we have 3 pairs of retroreflected light incident on the vacuum chamber, and that gives us the trap, and the anti-Helmholtz coils are out of the picture, and because the cross section doesn't show it. We characterize the mod using absorption spectroscopy. This gives us a size of the mod of around 500 micrometers and a temperature of around 500 microkelvin. In addition to the mod, we had the optical cavities. So we have the cross cavity design. We needed high reflectivity mirrors in anti-symmetric configuration. The curved surfaces of the mirror has 2 roles to play. They give us a small mode volume, which is good for coupling with atoms, and it also helps with alignment because we can work in the confocal regime. We also use PZTs to do the electronic actuation of the cavity. Now, how this complete system looks like is a bit busy. we have three layers. If we start with the central layer on the right-hand side, in addition to the Mott fields that I showed before, we have a probe field coming in, going through the horizontal cavity to the detection part. Looking at the top platform and the bottom one, this is for the vertical cavity. We first have to mode match, and then also after entering the vacuum field, we do the detection on the bottom. To characterize the cavities, we do a modulation of the light into the cavity. Unmodulated light has a Lorentzian profile. The modulated light has these side bands equal to the modulation. This allows us to find the line width of the cavities. For the horizontal, we got 42 megahertz. For the vertical, we got a 23 megahertz line width. This gives us a finesse of around 200. Now, how did we test that the cavities were coupled to the atom? I start explaining with the first way we did it in that I will call outside in. If we look at the horizontal or vertical probes into the cavity, if we change the power that is incident, we can thermally excite the atoms in the Mott and thus reduce the size and eventually eliminate the Mott. This can be shown that at 3 microns, we have a very healthy Mott, slowly disappears, and at 66 microwatts, it's completely gone. This was very useful in aligning the cavities, which you can imagine takes quite some time. Now, the inside-out method I will describe is about looking for scattering from inside the cavities into our detection. So these, we have different segments of the experiment. The first section is the probe light is on and incident to the field. Because we know the light exists, we can calibrate our detection. And as you can see, we detect a number of photons after they are attenuated quite a lot. Secondly, we remove the probe fields and only have the cooling beams on. This creates an optical molasses, and we see scattering from the cooling fields. Now, the question is, do we see only scattering, random scattering from all the different directions, or is it coming from the atomic cloud inside the Mott or the Mott chamber? If we add the probe fields, we see an addition of the 2 cavity modes. And finally, we switch on the Mott in the last window. Because we are just switching on the magnetic fields, there's no extra field. So at least since we have an increase of photons, we see that it's scattering and not only stray light if we didn't cover all the stray light successfully. We also did a simultaneous scan of the vertical and the horizontal. This is the scan with the probe only, and this is the scan with both the probe and the fluorescence. If we do an averaging over the different scans, we see these profiles in the horizontal and the vertical cavity. Now, this looks like a profile that we really wanted to look for. And let me go and explain this. The James Cummings model describes the interaction of a probe field and a single atom in a high finesse cavity. If we solve this equation in the interaction picture, we get an excited state energy level that is dependent on the cavity field and the tuning of the cavity atom system and the coupling between the atoms and the cavity. More simply, if we do it on resonance, we see this profile. As the coupling increases, the Lorentzian curve that is shown here in blue moves away, gets smaller, and we get side bands based on the coupling strength to the atom system. So now the question is this normal mode splitting, considering that the horizontal looks very much like the yellow field and the vertical looks much like the green field line in the graph. Unfortunately, after thinking about it and getting more feedback, we realized that since our cavities are scanning and not resonant to the atomic resonator, not locked, this cannot be the case. So we looked to a more generalized theory of scattering into cavities. So if the same setup is shown, but here this theory is based on a driving field that's perpendicular to the cavities and a cavity mode output that we measure. If we consider all the different properties of the system, we can get a line shape given by the following equation. This is a generalized Lorentzian, and important coupling factors are the G and the H that are shown here. The H is the coupling between the cavities and the cavity mode output, and the G is the coupling between the driving field and the atoms. Now, doing a solving of this analytical model using some simplifying assumptions, such as a high number of atoms, a constant linear density, and no off-axis atoms, and using the experimental properties of the cavity, we do see this shift in the output from a Lorentzian of the cavity only to an oscillating output in blue. We determined that we wouldn't see this oscillating pattern in the integrating measurements that we did. However, since the large difference in the center peak goes from a peak to a zero value, we do pick this up in the center. More also, once we do the same calculation with just changing the line width that we measured, we could get this rapidly oscillating output, and which corresponds, if we average again over it, we get a flat line that corresponds very well to this flat top that we see in the vertical splitting. I also have an update on this experiment. After being able to lock the experiment even through COVID times, lock the cavities, vacuum or Rabi splitting or normal mode splitting has been detected, as you can see in the graph on the right. So now that we have an infrastructure of lasers and atoms and two different systems, we are ready to work with bidirectional communication between the two systems. In the short term, that can mean that single photons can be extracted from the cavity system into the memories. In the long term, we are working to a two-mode phase-based processing node. Just in pictures, cavity can interact with the memories and also with home line detection, which can be used for quantum processing tomography. So how does this relate to the processing nodes that I talked about? So we are working towards double cavity EIT. For a single transition with two cavities, there is a Hamiltonian that is dependent on the atom, the cavity light, the light atom coupling, and the driving field that is on the outside of the cavity. Now, modeling the two systems, we have to use the tunings between the cavity and the atom and the laser field in the atom. When this is done, we see the following graph. This is a simplified model, but what I want to show is that we see an impact of the one cavity field on the other. So when the cavity 2 is detuned, we see an asymmetry in the splitted levels of the red cavity. Now, adding more fields and more levels gives us the N-type scheme that I showed before. The Hamiltonian is very similar. The atomic terms now just have the corresponding new levels. And we add the control field as a classical field, since this will always be very large. This is the same scheme that I showed this nonlinearity being created and the phase shift being created. But with adding the cavities, we believe that we can reduce the amount of signal field to the single photon regime. We also model this system and see a characteristic central peak that is due to EIT. This central peak is much more narrow than the line width of the cavity. So it's a better, higher coherence window of interaction. Again, we see an interaction between the two cavities shown here in blue and in red. So once a phase gate is realized using some kind of optically controlled nonlinearity, one can move to the important gates that is required to do a quantum processing node. So then the outlook there would be to do some processing or quantum simulation. Finally, I want to talk a bit about the entanglement source, specifically an integrated photonic source. So let's get a bit of a background of how we create single photons from nonlinear crystal or material. The process called spontaneous parametric down conversion takes in a pump field at 2 omega and gives 2 probe fields of omega each. Formally, this is the same as the difference frequency generation, where the vacuum fluctuation at omega couples with the pump field. Now, phase matching between the pump and the output fields are very important, and that's how we can increase efficiency. Now, why does this count as a single photon source? Energy conservation forces that each entering photon has to produce a pair of photons. If we herald on the one photon on the output, we can generate a single photon on the other output and check the statistics to confirm this. Now, the technological progress of this was as follows. First, Ball crystals were used in this method. Phase matching was or is achieved by different cuts or periodically poled crystals. Then edged or doped waveguides were started to be designed. Again, the phase matching can also be done with periodically poled or the nature of the dopants. Finally, can integrated photonics be used to do this generation, where the phase matching is done by the different phase velocities of modes in the integrated photonic device. So integrated lithium niobates promises a stronger confinement of the modes and therefore better interaction with the nonlinear medium. The spectral width of the modes are also limited, which is a good thing for applications. And both of these factors can lead to a higher pair production rate. So at ETH in the optical nanomaterials group, the fabrication of waveguides such as the SEM structure photograph on the left shows with widths between 0.5 micron and 1 micron. On the right, I show the layer structure. There's a substrate, the nonlinear material that's etched into a waveguide, and the cladding that can be silicon dioxide or air. So how we do an optical characterization is the laser light can be focused using a microscope objective onto the chip, and then it's detected using a lens fiber. How this looks is on the left-hand side is a chip, and on the right-hand side is free space. If we zoom in, you can see the slight scattering losses that we see along the waveguide, and finally the output of the waveguide. That's the bright circle. Now, one problem that also comes along with generating single photons on the telecommunication level is that there's a lot of background black body radiation. So you have to work on low temperatures. So there's two different ways that this has been done. The InCast detector shown here works at a temperature of -90 Kelvin. This is still not enough to achieve very precise measurements. The efficiency is only 25% and the background is quite high. So a technology that has exploded and had a lot of success in the last couple of years are the superconducting nanowire single photon detectors shown on the right. And I'll quickly go through the way this works. Nanowires are cooled to superconductivity regime, so we don't have any resistance and they are not ohmic. Simultaneously, this also reduces the amount of black body radiation to negligible small values. Once the photon lands on the nanowire, it removes the region of superconductivity. This instability causes that the regions alongside this excitation also become conducting, and a traveling transient current is created, which can be measured as a peak and therefore interpreted by fast electronics as a detection of a photon. So how we use this signal photon detections first was using a bulk source based on BBO crystal in order to replicate as much as possible the situation that we'll have once the integrated circuits are ready. So two different beams lasers are used in order to characterize the system. We have the pump that's at 775 for the single photon generation, but also a 50-60 nanometer laser to generate for alignment purposes, but also to generate second harmonic generation, which is just the opposite process of SPDC, and therefore helps with the alignment of the crystal. Different polarization elements are used to change the intensity of the fields, but also to match the polarization that's required for the crystal. Focusing is very important in order to also, again, allow for phase matching and good interaction with the medium. Finally, attenuations are in different sense. The bandpass filter and the notch filters are used to attenuate stray light that comes from the pump field. This is sent to a fiber polarizing beam splitter and interpreted with the electronics from the detector. So this picture, there you go. It gained a shadow for some reason. So what we managed to achieve with the bulk source is that we did a self-correlation function of the two output photons, the idler and the signal. This is a bunched light source, and this correlation coincident measurement can be used to measure certain properties of the source. Again, an update. Detections have been used to characterize the pair production rate and also the coincidence versus accidental rate. Improvements in the waveguides have also been made. Phase matching is still a problem and a lot of simulations are going on, but I hope you can see, even though it's very faint, there's racetrack resonators that are being created in the waveguides. The resonators increase the interaction time between the pump and the medium, which can improve the source quality and also shape the line width that one gets, and typically much narrower than just a straight SPDC production. So with that, I want to conclude. We have an example of a photon source that can be integrated and has promising future. We have a platform that can develop into a quantum processing node. And finally, back to the start, we have quantum memories that are scalable because they work at room temperature. And just to show you what this picture highlights is we have 2 memories on the table and then 1 in a rack mounted, so it's much smaller. But there's more news there. A company, QNEC, that was founded by members of the group, has been working hard to commercialize this technology and even getting it smaller. And yeah, if you have any questions, yeah, they've had quite a bit of success to get some funding to do this. Yeah, so that brings me back to the quantum repeater, the important part that we need to get to long distance networks. And hopefully I've convinced you that we are making a lot of progress in different parts of these systems. Finally, some publications that have resulted in the work that we've done. I didn't talk much about the processing characterization, or an interesting paper we did on quantum simulations using the room temperature memory system. And therefore, I want to thank everyone that helped. Everyone in the groups always assisted, but specifically the people in bold and whose pictures they are. My PhD advisor, Professor Eden Figueroa, in the red block, and my postdoc advisor, Professor Rachel Grange. And with that, I also thank you for your attention and would welcome any questions.
Thank you, Dr. Jordaan. I must say that was a very impressive talk. We open the floor to questions, so you can either use the Q&A feature, or since there's not a lot of us, you could raise your hand and we could allow you to pose your question live.
Yazira, maybe while people think about their questions, I also wanted to thank Bertus for a very nice talk. And in particular, it's really nice to see that what he did could potentially be a very good match in our reality, yeah? Because I think we should have most equipment that you need to pursue your direction of research, and I think it would fit very well with what Yazir and others are trying to achieve in our labs. Yeah, no, excellent.
So there is one question in the Q&A. Thank you, Bertus, for an excellent presentation. Please, can you explain to me how you generate entangled photons in the single BBO crystal shown in your setup? Did you entangle the single photons generated via the BBO with the classical light of the second laser, which is at 1,555 nanometers? Or something around that range?
Yeah, so no, the answer is that the setup is way simpler than that. When we generated photons using the 775 nanometers, that was the only light that was on. So just a simple SPDC experiment where you get 2 photons out for each input photon at double the frequency. So the 1550 was just used for alignment, as I mentioned, for second harmonic generation. I mean, the second harmonic generation is much simpler to detect, and you can sometimes see it in the crystal shining if you have a pulse laser, for example. We had both, first a pulse laser and then a continuous wave laser. And then, yeah, so that's it. No entanglement between the 1550 classical light and the quantum light.
Thank you. Are there any more questions for Dr. Jordaan? There's an attendee with their hand up, so I'm just going to allow the person to pose their question live.
I think there is a question in the Q&A, Yazira.
That's the question okay, there's another question. So while I allow the question for Professor Conrad, I'll just ask Dr. Jordaan to take that question in the Q&A. This is from Camille. He says, great talk. Can you come back on how EIT-based quantum memory degrades with time?
Okay, so let me, oh, my screen is not shared anymore. I'll share it once I find the applicable slide. Okay, so the storage of the light is limited by the coherence time of the dark state polariton that is created by the EIT. So what the dark state polariton is if you again solve this equation in the interaction picture, you find that one of the energy or one of the potential states is a combination of the two ground states without any population in the excited state. So that's why it's called a dark state. There's fluorescence cannot happen or decay cannot happen from that. Now, for this to stay there, the atoms have to be pretty protected in some sense. So a lot, obviously in cold atoms that happens because there's no velocity of the atoms. However, in the room temperature experiments, you can imagine that once the atom hits another rubidium atom, this causes a disruption of this coherence and you lose that. So what the buffer gas does is it puts in, for example, neon, that is a nonpolar atom. So it doesn't do elastic scatter, or it doesn't do incoherent scattering with the rubidium. So the more you increase the buffer gases, the rubidium atoms don't see each other, and therefore they cannot decohere each other. Another thing that also happens is the sides of the cell, of the vacuum cell, gets coated by an organic material such as paraffin. And again, that reduces scattering against the glass collisions against the glass. And that also enhances the coherence time. And with higher coherence time, you have longer storage.
Okay, thank you. There's a question by Thomas Conrad. So I allowed you to speak, so you can pose your question directly to Dr. Jordaan.
Thank you, Yazira. Yes, hello. My question concerns also the quantum memory. Did I understand correctly that you used two paths, like a dual rail, you called it a dual rail qubit, to separately treat the horizontal and the vertical polarization?
Yeah, that's correct.
Okay, and can you also think of you know, maybe having spatial modes that you store there? I mean, in some sense, they would that would correspond to a whole cloud that is now distributed over a transversal area, and then if they emit in coherence, then maybe one could get back the spatial mode. Would that work?
Yeah, so I mean, there is definitely, this has been shown using an EIT medium, an EIT memory, to be possible. Though I'm not very completely, I don't know what the word I'm looking for is. I'm not fully aware of the specificities of the experiment. They've stored these orbital angular momentum modes, for example, in a similar process. They change it into a dual rail system using EIT. They store it and then they recombine it afterwards too. So this was done in the Julien Lerat group in Paris.
Okay, and is it like also possible at room temperatures? This
was done in cold atoms. So yeah, one would, I mean, if you just map the spatial mode onto a polarization mode, or and then dual rail, or just immediately, yes, then I don't see a reason why it cannot be done. However, that experiment was done in cold atom.
Thank you.
Okay. Perfect. So thank you so much. If there is no more questions, I'd like to hand over to Professor Francesco Petraccioni.
Yeah, hi, sorry. I couldn't find the mute thing, it just disappeared. Yeah, no, Bertus, I think then it's my pleasant duty to thank you very much for a very nice talk. And it was really great to see what impressive work you've done over the years. And I can promise you that we will make a big effort to get you back in the South African academic scene, yeah, because you will be able to make a big contribution, yeah. In particular, you mentioned at the beginning our SA quantum technology initiative. And that you couldn't find much information online. I'm very happy to share with you the roadmap, yeah. The PDF of the roadmap, and you can see what we have in mind. Yeah? So it will be, it's not a secret document. It's just that I think it's not online somewhere. Yeah, but I'm very happy to share it with you. Yeah. So Berto, thank you very much. I'm sure we will stay in touch and maybe have another conversation offline. Either this week or early next week, yeah. And I'm sure Yazira will organize it, yeah. So thank you very much, everyone, for attending this afternoon. And again, thank you, Yazira, for inviting Bertus. Thank you, Ilya, for being the usual co-host. And thank you very much, Bertus, again for your time and for a very interesting and well done presentation. Thank you very much. Thank you.
Thank you very much for the
good afternoon. And stay safe. Yeah, thank you.
So,
bye.
bye-bye.
Thank you.
Bye-bye.